example coming up. Here was our multivariable second derivative test. So just to review and have it here at the beginning, we're going to begin by finding our critical points A, B. That's where the first partial derivatives both equal 0. This is going to take the most time. Just finding these critical points, actually from all of it, I mean, it looks really intimidating, but that takes the most time in this test. Sometimes, though, it does go very quickly. Then we're going to take all of our second derivatives like so and plug those numbers in, and then do our calculations and see where we land. Okay. Here's our first example. Find the local extrema. Let's look at f of xy equals 15x squared minus y squared minus 10y. Okay, so where do we start? Well, we need those first partials. And so I've got them right here. Notice also I'm using some shorthand notation. So for the derivative with respect to x, I'm just going to write f sub x instead of f sub x of xy. Repeating that x of x comma y every time gets to be a lot. You see this all the time. People just write f sub x. We know that means the derivative with respect to x. Same thing with f sub y. So I'll be doing that from now on. Well, what is the derivative with respect to x? Well, 15x squared. That's going to go to 30x. Derivative with respect to x, remember the y's are constants. And so both y squared and 10y are constant, and so those go to 0. All right, fy. Well, that derivative, here the x is constant, so that goes to 0. Negative 2y minus 10. Okay, so far so good. We noted in our test that we need the values where these both equal 0. So that's not going to be too difficult for this example. So we set each derivative equal to 0. And we're going to be able to solve for x and y rather quickly. This did not give us too much trouble at all. Solving fx equal to 0, we get x equals 0. Solving fy equal to 0, we end up with y equals negative 5. So we know that this one point and this one point only is a critical. 0, negative 5 is our only critical point. That point causes both derivatives to equal 0. Okay, this one was rather simple. We're going to do a harder one in the next video. Let's keep going. What do we do now? Now that we know all of the critical points, we need to find those second derivatives, right? So I've done that here. Again, these went pretty fast in this example. So as we look at fx, another derivative with respect to x, fxx, and we get 30. We're also going to use that to get fxy. Well, this derivative with respect to y is simply 0. And finally, we look at fy. We take the derivative with respect to y again, and we get negative 2. So again, very simple. I mean, these all ended up just being constants. So what do we do next? We're going to plug, and I'm showing you a lot of work here, but we're going to plug our critical point into all three of these. And that's our values of A, B, and C. Now, of course, all three of those second derivatives are just numbers, so there's not anything to plug in for x and y. If these had x and y, we would plug those values into them, obviously, but they're not, so we just get the same numbers, 30, 0, and negative 2 for A, B, and C. Okay, So then we're going to find AC minus B squared. A times C minus B squared. I've got it right here. And we got negative 60. Okay. So at this point, we'd go back to the theorem. We'd say, all right, we got a negative answer for AC minus B squared. What does that mean? Well, it turned out that was actually the one where we can just stop at that point. If AC minus B squared is negative, we know we have a saddle point at f of 0, negative 5 at our critical point. We don't want to finish, though, just yet. We want to know the z value. So that's our critical point, but we always want to go back and plug that into the original function to get the ordered triple here. Same procedure as when it was in one variable, right? A couple chapters back. So we're going to take 0 and negative 5 and plug them in for the x and the y. So we'll have, going back to the original function, 15 0 squared minus negative 5 squared minus 10 times negative 5 gives us negative 25 plus 50, positive 25. And so we can say that there is a saddle point at 0, negative 5, 25. Okay. And that's the end of this example. You notice my note here. Check out some 3D calculators online. 3D graphing calculators, I should say. There are a lot of really cool, handy, free ones. There are a bunch. If you Google 3D graphing calculator, this one comes up first for me when I Google that. The one by Geogebra. And I've played around with some of them out there. I actually find this one to be the best. So I want to show you guys what it can do. And I don't know how well this is going to come across for me filming here, but I'm just going to grab my camera and see if I can situate this correctly. Okay, so that's my computer screen. Here's the video. Let me just kind of tuck that out of the way. So when you go to Geogebra right there, 3D calculator, I've got some stuff entered here, so I'll show you what that's all about. But it shows me this X, Y, Z plane, right? So here the red is the x-axis, the the green is the y-axis, so x-axis, y-axis, and the blue is the z-axis. So I went up here, and this is actually the second example we're going to do in a minute. Right up at the top, I typed in z equals 15x squared minus y squared minus 10y. Very simple to do, very user-friendly. And let me highlight it now. So there's the graph. These things tend to look a bit overwhelming when you see the graphs. So this is done in red, but it's infinitely tall. It's got this kind of weird structure. It's kind of like an X shape. So if you notice over here, there's this gap right there in the middle. So it's like it's curling in. There's kind of a parabola going on right there, and then a space, and there's another parabola, but then it's it's arching up, and it actually connects over the top. So let me kind of show you what we just found. So we found this point right there. That's our local extrema, where it all comes together there. Turned out that was a saddle point. It kind of looks like a local, maybe like a local max or something, or a local min. Right now, let me highlight that point right there. So what's going on? How is that a saddle point? So if we're looking, and just how did that get found? 0, negative 5, 25. So the x value is 0. Then we counted backwards 5 on the y and up 25. So 0 on the x, negative 5 on the y, 25 on the z. So what is that? Well, you notice in the y direction, in the green direction, that's a maximum. If we're moving along the y, that's at a peak. But if we move along the x, it's a minimum. Let me show you. So let me spin this thing this direction so we can see through, that kind of that gap in the middle. So along the red axis, and it's hard to see, and if I suspicious if I zoom out, but it's very skinny, but as it goes along the X it dips down. Oh, okay, we kind of got that as I like highlighted the point. So it's at a minimum on the X, but at a maximum on the Y, and we've got our saddle point there. Okay, that's all I wanted to do for this video. I'll see you in a more difficult example.